Hello to all. In this lecture, we will study about carbanions, and in this lecture, we will go with the flow with initiating the lecture with the structure of carbanions, and then we will see some methods to generate carbanions, and then we will see the reactivity of carbanions, and at last, we will see some reactions involving carbanions. So these are our targets for today's lecture. So first, what is the structure of for carbanion? A simpler carbanion we can show is this is a simpler carbanion. As you can see, this is sp3 hybridized, and in geometry terms, we can show that this is a carbanion. So when there is when there is interconversion between two carbanions, it will look like this. So the geometry for this carbanion is pyramidal. As you can see, there is pyramidal shape in this particular structure, and in first case it is upward, and in second case it is downward. As you can see, that pyramid is of this shape. This carbanion is also like this pyramidal shape. Okay, because it is forming a pyramid. These two electrons are upward from the base of this whole structure, so it is creating a pyramidal shape. So in this carbanion, there are 8 electrons in outermost shell. As you can see that 2, 4, 2, 6, 2, 8. There are 8 electrons in outermost shell. Now, generation of carbanions. Generation of carbanions. This first method is abstraction of proton. Abstraction of proton. How we can abstract a proton? Suppose this is RH, and if we abstract this proton, we will get a carbanion. As you can see, so proton has been abstracted from this, and we are left with R negative, that is carbanions. Second method in this list is decarboxylation. Decarboxylation. How we can how do it? Suppose we have a carboxylic group here. So what will happen that this electron pair will go here to form a double bond here, and these electrons will go to R, and we will get R negative, that is carbanion plus CO2. This is how decarboxylation works. Our third method is attack by a nucleophile. Attack by a nucleophile. As you know that nucleophile is a species which is trying to finding the nucleus or positive charge. So how it will work? Suppose we have an alkene. So when we make it happen to attack a nucleophile on this particular molecule, suppose we have Y negative nucleophile. So what will happen? This Y negative will attack here, and this double bond will be broken up, so that these electrons of double bond will go on this carbon. As you can see that here the two electrons on the nucleophile will attack here to form a bond with this carbon atom, and electrons from this particular bond will go on this carbon atom to form a carbon ions. Our next method is formation of organometallic compound. Formation of organometallic compounds. For example, we have alkyl halide and we take a metal, for example M. In the product we will get RMX. This is the organometallic compound. As you can see that this metal is connecting the alkyl group and the halide group. Earlier in the reactant, the alkyl group was positive charge and this halide group was negative charge. But in the product, when we made an organometallic compound, this alkyl group will also be having a negative charge and this halide group will also be having a negative charge. This is the property for organometallic compound, that metal in organometallic compound will act as a positive charge and alkyl group and halide group will obtain a negative charge. So yes. So in next step in this particular reaction, when we react with alkyl lithium, what we will get? We will get that R negative is separated and MX. So we got carbon ion. This is carbon ion. So this is how, by formation of organometallic compound, we will get a carbon ion. Our next method is how halides act as carbon ions. So how we get halides? Suppose we have triphenyl phosphine. When we react triphenyl phosphine with alkyl halide, for example CH3Br, what we will get that this will make a organometallic compound as so this is the reaction for this, and this is forming an organometallic compound. As you can see that there is triphenyl phosphine is reacting with alkyl halide to form this organometallic compound, and in this further, if we react with RLi, alkyl lithium, we will get a carbon ion. What happened here is that this is halide. This is halide that we were discussing earlier. So how we can obtain halide? So what happened that when we react triphenyl phosphine with alkyl halide and then further treating the product with lithium alkyl, we will get halide as an carbon ion. Another method to obtain carbon ion is using dithiene. How we can use dithiene to obtain carbon ion? Let's see. So what we'll do that we will react a carbonyl group with a dithiene in the presence of CHCl3 and HCl in gaseous form, so that in product we will get a compound like this. Further, when we treat this product in the presence of THF and in negative 40 degrees Celsius, we will get a carbon ion. There. This is how we can obtain a carbon ion about stability of carbon ion. In stability, we will see certain factors. First one is inductive effect. So, positive inductive effect will lead to less stable carbon ion, whereas the negative inductive effect will lead to more stable carbon ion. Suppose, for example, we have this carbon ion. So this carbon ion will be less stable than if we have a fluorine attached to this carbon. So this will be more stable because of negative I effect, and this is less stable. Further, if we have two fluorine atoms attached to this carbon, we will get a more stable carbon ion because of the negative I effect. But suppose we have positive I effect. For example, this is alkyl group and these are two hydrogens, and in next structure we have two alkyl groups. So which one of these will be more stable? This will be more stable because in this particular structure we are seeing that there are two alkyl groups and alkyl groups are providing here positive inductive effect. So this is why this will be more stable. Second thing we will talk about in stability is a resonance effect. Resonance effect. So molecules which will have resonance in their structure will be more stable than the normal molecules. For example, this will be more stable than simpler toluene. So this will be more stable. Why? Because of the resonating structures uh, available in this case. So I will draw one or two resonance structure in this case. What will happen that these two electrons of negative charge will go here to form a double bond here, and this double bond will go to on this position to form a negative charge here. Let's see how. Further, you can draw more resonating structure in this case. So this is resonance effect. In the presence of resonance effect, the whole structure becomes stable than the molecule not having resonance. Now, more is the S character in the molecule, more it will be stable. For example, sp3 hybridized will be less stable than sp2 hybridized, and it will be less stable than sp hybridized. So as you can see, there is more S character. This is more stable of these three molecules. Reactivity of carbon ion, we will talk about two reactions. First one is displacement reaction. In displacement reaction, suppose we have a carbon ion and we react it with this molecule, what will happen that H positive will displace this negative charge over here to form so this is displacement reaction. Elimination reaction, what will happen that suppose we have halide group attached in on this position, and when we react our nucleophile will take up one of the hydrogens, and the electrons from this bond will go to this position to form alkene, and it will eliminate the halide group from here. So in product we will get an alkene. We will get an alkene. Now we will talk about some reactions involving carbanions, and one of those reactions is Aldol condensation. In this reaction, there is a reaction of aldehyde or ketone in the presence of acid or base to give us beta hydroxy carbonyl group. For example, suppose we have CH3COH, and in the presence of base, there will be a nucleophile attack at this position, and we will get carbanion. So this is a carbanion, and now what will happen that there will be further a nucleophile attack from this carbanion to this reactant. So there will be a nucleophile attack, but not here. This time it will be at this position. So in product we will get, first see, when there is a nucleophile attack on this carbon atom, what happens that these electrons go on to oxygen, and we are left with this structure. So now what will happen that in the presence of H2O, it will give a proton to this oxygen, so that we can get OH group here, and further we will get CH3 COH CH2 C double bond OH. So this is a beta hydroxy ketone. This is beta hydroxy ketone, because this is beta position and there is hydroxy group and there is ketone on. So yeah, this is all about Aldol condensation. Our next reaction is Claisen condensation. In Claisen condensation, we get beta ketoester from carboxylic ester. For example, we have CH3COO-C2H5. This is carboxylic ester, and in the presence of base, there will be a nucleophile attack on this carbon atom, so that we get CH2 negative COO-C2H5. So now further, there will be a nucleophilic attack, again CH3COO-C2H5. So again there will be a nucleophilic attack, but this time there will be attack on this carbon atom. So in product we will get CH2COO-C2H5, and here we will get COCH3O-C2H5. Sorry, because when there is a nucleophilic attack on this carbon atom, the electrons from this double bond will go on to oxygen, forming a single bond here, and the negative charge on oxygen. So in next level, what will happen that these electron pair will go to form a double bond here, and this will be released from here subsequently. So finally we got CH3, C double bond O, CH2, C double bond O, C2, H5. So this is nothing but a beta ketoester, because this is beta carbon atom, beta keto ester, beta keto ester. So this was all about Claisen condensation. Our next reaction in this list is Dieckmann condensation. Dieckmann condensation. In this reaction, by using diester, we get cyclic beta ketoester. Suppose we have a diester in the form C double bond O CH3, and here hydrogen, and at this side also there is a ester. So now, in the presence of a base C2H5 O negative, for example, there will be a nucleophilic attack at this carbon atom, so that one proton will be lost from this position and forming a carbanion at this position. So in the next step, what will happen, that the electron pair from this position will go to form a bond at this position, and the electrons from this double bond will go to on this oxygen atom in such a way that in the next step, this electron pair will come to form a double bond here and releasing this portion of structure. So we are get finally we get cyclic beta ketoester in the form so this is cyclic beta keto ester. As you can see that this is beta position, this is ester. So yeah, this is all about Dieckmann condensation. Our next reaction is Michael reaction, and in Michael reaction there is addition of carbanion with alpha beta unsaturated carbonyl group. Suppose we have carbanion C double bond O C2H5. So this is a carbanion, and we react it with alpha beta unsaturated carbonyl group. Now there will be a nucleophilic attack from this carbanion to this position, so that in the product we will get C2H5 COO C double bond O CH COO C2H5, and here we get CH2 CH2 C double bond CH3. So this is Michael reaction, in which there is addition between carbanion and alpha beta unsaturated carbonyl group. So yeah.
Next reaction is Fabroski rearrangement. The rearrangement of cyclopropanone and alpha haloketone in the presence of base to carboxylic acid derivative is known as Fabroski rearrangement. In this reaction, we take alpha haloketone and in the presence of base, nucleophilic attack is on hydrogen. When we take a nucleophile here, nucleophile attack on this hydrogen, and we get the carbanion, and this carbanion further react at this carbon, excluding the chlorine atom from here, and sorry, there it was oxygen, double bond oxygen, because it is ketone. And in next step the hydroxide react at this position, and electrons from double bond goes to oxygen, therefore making it O negative here. And now the electrons from O goes to make a double bond here and opening this little ring, and thus we get carboxylic acid derivative here, and further this negative charge will be taken up by the water molecule, because H will take it, and H will be attached to this ring to form a carboxylic acid derivative. So this is Fibrovsky rearrangement reaction.